In this video, we will be looking at the geometric distribution. Two essential questions. What are the criteria for a geometric distribution? And how do we calculate geometric probabilities? 1. Two outcomes. 2. The probability of success is constant. And 3, the trials are independent. These three criteria are exactly the same as with our binomial. And these three criteria make up what are called a Bernoulli trial. A Bernoulli trial satisfies two outcomes: probability of success is constant and the trials are independent. Separately, we have a fourth characteristic of a geometric distribution. Same as binomial. These first three, same as a binomial. The fourth characteristic that separates the geometric from the binomial is that in this case we are going to try until first success. Previously, with our binomial, the number of trials were fixed. So with our geometric, we will try until our first success, unlike our binomials, where n is fixed before we begin. Let's now take a look at the formula. This formula can be found on page 415 of your text. It says the probability that cap x is equal to small x will be equal to 1 minus p, that's the complement, to the power of x minus 1 times p, the probability of success. The mean or expected value of this variable, of this geometric distribution, will be 1 divided by p. And the standard deviation will be the square root of one minus p, that's the complement, over p squared. Now all these formulas here unfortunately are not going to be on the formula chart. I would say don't fret, because you're going to soon see that they are pretty easy to come up with on our own. The standard deviation we will rarely use, but the probability and the mean we'll see that they make perfect sense. Let's look at an example from your homework. Example number 3 on page 430. Pause the video at this time, open up your text to that page, and read that problem a couple times. Example number 3 on page 430. Parts A, B, and C here involve a simulation, and so I'm going to leave it for you. No, you should probably use your calculator to draw some random numbers, and you're going to need to assign particular values to those random numbers. I'm going to get on to D, which says calculate the actual probability model. Okay, what we're dealing with here is this LeBron James situation with opening up boxes of cereal and looking for his picture in it. And it says 20% of the boxes will have his picture in it. We're going to define X to be the tries until the first success. That is, how many cereal boxes will we need to open up until we get a picture of LeBron? X equal 1. That is, our first success happens on the very first try. Note that different from our binomial where X could be 0, we could have 0 success out of 5 tries, but this is the tries until our first success. It doesn't mean anything to say our 0 tries. You actually have to try until you have a try before the first success. So X equal 1 is our minimum. Well, I'm going to use this method we've used before, 1 blank. This is my very first attempt. I'm saying that very first attempt is a success. Well, what's the probability of success in this case? It's 0.2. What we're saying is there's a 20% chance that my first success comes on my very first attempt. Well, X could be 2. What we're saying here is our first success is on the second attempt. So here I come, 2 blanks. If my first success is on the second attempt, then clearly the first attempt was a fail. Then the second attempt was a success. Well, what is the probability of failure? It's the complement of this 0.2. It's 0.8. And then my success would be 0.2. Now to find this compound probability, we simply multiply. And means multiply. It's legitimate to multiply because we know these events are independent. 0.8 times 0.2 is 0.16. Let's look at the event X is 3. We're saying the very first success occurs on the third try. So now I have 3 blanks. We're saying it's going to be a fail, then a success. Well, these 2 fails are both 0.8. And this success is 0.2. And this product is 0.128. Notice that this is decreasing each time. That makes perfect sense because the only difference between each one of these is another 0.8 multiplied by. That is, we're taking 80% of the previous number. No matter what the probability of, no matter what P, the probability of success is, when you're going to have the greatest probability for your first success is on the first try, because thereafter it's going to be compressed by that complement. Now let's look at X equal 4. This is our first success comes on the 4th try. Let's skip the blanks and just go right for the letters. In this case we're saying fail, 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 success. Well, that's 3 0.8s and a 0.2. Let's just write this as 0.8 to the power of 3 and then 0.2. Fail, 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 succeed. And this value is just 80% of that previous number. And that is 0.1024. Now let's see if we can use the formula that we saw previously, this formula here, to arrive at this same probability. Well, the formula says the probability that X is equal to some value, in this case 4, the probability that X is equal to 4 is equal to 1 minus P, in this case P is 2 for us, 1 minus, 0.2, X minus 1. Our X is the number that we're talking about here, this 4. 4 minus 1 times our P, that's our probability of success, 0.2. Well, 1 minus 0.2, that's 0.8. 0.8. 4 minus 1, that's 3. And here we still have this 0.2. So you can clearly see that this quantity here, 0.8 to the third power times 0.2, is the same as what the formula arrived at. So our formula, while it is true, it's pretty easy to think about. Now let's see if we can find our mean or expected value. The mean of our random variable x is going to be equal to 1 divided by our probability of success. In our case, it's 1 divided by our probability of success is 0.2. Well, that's a 1/5. 1 divided by 1/5 is 5. What we're saying is our long run average for our first success is 5. If we do this process over and over and over again, pulling out boxes until we get the first success, in the long run, the average number of boxes we'll have to pull out is 5. That makes sense. 1 out of every 5 boxes will contain LeBron's picture. With this information, you should be able to answer the rest of the questions from this chapter.